direct comparison test. Go ahead and just pause this, copy down those steps right there. Got some nice, neat, colorful steps for you. I know it looks a little tricky right now, but I'm about to make it make sense. I'm about to make it easy for you there. The good news is there's not really much work that we need to show, but the work that I need to model for you, you need to write that down. All right, so direct comparison test. We're going to start out the same way as a limit comparison test, as we're going to find a comparison series, and we're going to write down what that does and why. Now, most of the time, that comparison series will be an easy piece series or an easy geometric series, maybe an integral test or something like that. It could be a few different things there, but it's usually something that we know what it does and why. The thing is, when you choose a comparison series for the direct comparison test, you want that comparison series to look as closely as possible to that original series as you could possibly make it. And then this proof part is going to work really well. Now, what we're going to do, we're going to have known these inequality things, right? We're going to have to show something. That word show, that's important, right? You're going to need to show one key step in here that sometimes students mess up on. I'm going to show you how to do this correctly. Let me just kind of mention this, and then I'll show you what goes on in my mind, how I remember it versus having it memorized, right? If our comparison series converges, what we need to show, that the original series is smaller than the comparison one. And if we can successfully do that, that means they both do the same thing. So since that one converged, the original one will also converge. If the comparison series diverges, we need to flip that around. We need to show that the comparison one is the smaller of the two. And then if we could successfully show that, that means they both do the same thing. So since that one diverged, that means the original one is also going to diverge. Now, here's how I remember that. So you could just memorize it, but here's how I actually remember it with the understanding, right? Let's look at this bottom one. If B sub n diverges, that just means a list of numbers. Diverge means it's going to shoot to infinity. So like here's our B sub n, and that's just diverging. So that's shooting up all the way to infinity, right? There's my B sub n. Now, if I can show that that's the smaller than the original one, which means the original one is bigger than that. So if the B sub n is the smaller series, that means the A sub n is larger than that. Well, think about it. If the smaller series is going to infinity, that means the bigger series will also have to go to infinity, right? So if it was flipped around, if A sub n was the smaller series, I wouldn't know what it does. So if B sub n went to infinity and A sub n was smaller than that, that means it might be going to a number smaller than infinity. It might be converging to a smaller number, or it might also be diverging. It might also be going to infinity just at a slower rate right there. So you don't know what it does if you flip those around. So that's kind of how I remember it. If B sub n diverges, goes to infinity, and I know that if the other one is larger than that, then that's also going to prove that it also has to diverge. All right, similarly speaking, if B sub n converges, so here's my B sub n. Converge means it's going to narrow down. It's going to get closer and closer to a number. It's going to get closer to 4. It's going to get closer to 0, whatever, right? So here's my B sub n converging to some number. And if I can show that the A sub n is the smaller series, now it might not be true at the beginning, but you're concerned with as you're approaching infinity. So sometimes if we plug in a couple numbers at the beginning, it might not be true. So maybe A sub n starts off and it goes above there, but then eventually it goes below and it goes below as you're approaching infinity. And here's my A sub n. So if your B sub n narrows down and converges to a certain number, and your A sub n is the smaller of those two series, so A sub n is smaller than that. So if B sub n converges to a number, then if A sub n is the smaller one, then that would also force that to converge, because it can't diverge, go to infinity, because then it's the smaller series. So it'll like bump into that like a ceiling right there. So you got to show that the A sub n is smaller than the comparison one. That means they both do the same thing. That one's also going to converge there. So hopefully that kind of makes sense clear, because sometimes I kind of forget what's going on. I just think about this real quick, and I know that's pretty much where I closed my eyes and just thought about that in my head, and I wrote those notes down in the proper way. Sometimes people just think it's quicker to remember if I get converge, show the original one is smaller. If I get diverge, show that the comparison one is smaller. So if it's a little bit quicker for you to memorize that, I would like you to understand kind of what's going on right there. And then here are two examples where I would use the direct comparison. So let's just work through the two examples here, and then I'll try to address the biggest question I always get. How do I know whether to use a limit comparison or the direct comparison? I'll try to address that right now and again at the end. But limit comparison, remember those notes. is, those work really, really well when you have like rational functions with the polynomials, stuff like that with the polynomial stuff on the top and the bottom, or even if you have radicals and stuff on the top and the bottom. But we've done limits with those things very well. Sometimes you got to involve L'Hopital's rule, your pre-cal properties, but I'll use them in comparison. I typically will use direct comparison. If I can make that comparison series look very, very close to that original one, that direct comparison has a shot at working. Doesn't mean that it will work. It might be inconclusive. I might have trouble proving it and I can't get that to work out. I might do the limit comparison on that one. Or here's another instance where I would jump straight to the direct comparison, because we haven't really done limits with, when I have like n to the third, n to the fifth, like the easy polynomials, the limit comparison works really well. We've done limits with the polynomials like forever, right? But if I have a number raised to a variable, we haven't really done a lot of stuff with limits with that stuff there. So what I would do, and if you have to involve L'Hopital's rule, it gets messy or stuff there. So when I see something like this, I would prefer to use the direct comparison on that one, right? So let's just go through the nuts and bolts, and then we'll try to address that question again at the end right here. Okay, so both of these I'm going to use direct comparison on. So I got this thing, I'm going to write down my comparison series. Now when I'm choosing that comparison series, I'm not just going to do the 1 over n squared. I'm going to choose the 1 over 3n squared as my comparison series. Now you're going to see why this works out so very well in a second. But that's the same thing as like, you could allow to pull out the 1/3 and you got a 1 over n squared, all right? So that p is equal to 2. That is a convergent p series. All right, so I did what we normally do. I found the comparison series. I wrote down what it does and why. And now I'm one of these two stars right here, where I'm one of these two stars. So since this is a convergent p series, and that's why it's kind of important, it's kind of tragic if you don't know your p series, because then you're missing your easy p series stuff on the test, and you're also missing this stuff, and it's messing you up on all the comparison series as well. So you got to make sure you have memorized. Half the battle is just memorizing what your tests say and make sure you got that down, right? So since this converges, I'm on this purple star right here. So if b sub n converges, I need to show that the a sub n is less than the b sub n. So I'm first going to write that down. Remember, this is your a sub n right here. That's your original problem. And this is my b sub n right here. So I need to show that the original series is smaller than the comparison series. Now, very important, all right? That word show, you can't just write it down and say that it's true. Sometimes it might not be true, okay? So if I just write down 25 is less than 20, just because I wrote it down doesn't make it true, right? Hopefully your brain just got a little like cramp right there, like, oh, I do not like that. That's just completely wrong, right? It bugs me that I wrote that down. But just because you write it down doesn't mean that it's true. We have to show that this thing is true. Now, to show that one fraction is smaller than another fraction, right? Let's just compare this, all right? This isn't part of this example there. But if I needed to show or reason out why 1/4 is less than 1/3, we could do it like this. We could say that this is true. If the numerators are the same, you can say that this is true since that 4 is bigger than 3, all right? This step right here proves that this is true right here, because if you're going to divide a pizza up among 4 friends equally, and then you're going to divide that same pizza up among 3 friends equally, you're going to get a smaller slice of the pizza, a smaller slice of the pie. So 1/4 is less than that 1/3. You're going to get a smaller slice of the pie right there. So I just wanted to show you that with just basic numbers. But if I write down the, hey, reason out why this is true, yeah, the numerators are the same and that 4 is bigger than 3. We need something like that, right? We need something like that to justify why that thing is true. So that's what the key step right here. So 1, we'll write it down, but then you got to show that it's true. So here's how we're going to show it's true. So that's why we want those comparison series to be practically identical to each other, because look how close those are. And this proof part of the problem works really well when they're close to each other. So notice that the numerators are the same. And this one, they're this identical except for that +2. So that +2 is making this the larger friend group that you're going to divide this pizza up with there. So I'm just going to write down this very key step. You have to write this down. This is true since the 3n squared plus 2 is greater than that 3n squared. So there's our comparison series. And then we have memorized that, hey, we're working with this guy right here. So I write that down and then show that it's true. This step right here justifies why this is true. So if you could successfully show that that's true and that all is kind of making sense right there, that means both series do the same thing. So that's why I have you write this down. So it's less thinking at the end of the problem. So since this one converges, that means the original one will also converge. So I'm going to write down converge. And then the test that we're using, we always write down converge or diverge. And then you tell me what test that you're using. That's the direct comparison test. Don't put DC, that's like some comics and stuff like that, or the nation's capital. All right, we need to worry about, we're just going to put direct comparison. All right, so write that down. Don't do your made up tests or made up abbreviations right there. All right, so just common mistake. I remember each year when I grade the homework, there's at least like 5 people that do not have that step in, and they have this and then they have this, and that's a humongous deduction. Don't do that on the homework. Don't do it on the test. I just stress that so much right there. You just watch the video, just model that. Notice that there's not much that we have to write down here. Write down your comparison series, what it does and why. Write the inequality down. Justify why that inequality is true, and then converge or diverge, tell me the test you're doing. It's very short work that you got to write down there, but everything I have written down there is necessary. You got to get that down. All right, let's just do, I usually just do that example for the notes there. Let's just do an extra example, but this is another one where I would jump straight to the direct comparison on there. Here I did it because that comparison series looked very, very similar, and I got the proof to work out. Now, sometimes the comparison series will look similar, but I can't get the proof to work out like that, and I'll jump back straight to that limit comparison because I do have some polynomials right there. All right, so on this comparison series, I'm not going to have a P series here. I'm going to use 3/5 to the n as my comparison series. That is the same thing as 3 to the n over 5 to the n. But we do know what this does. This is my r is equal to 3/5. That is a geometric series. And remember, that's in between -1 and 1. That is going to be a convergent geometric series. All right, so I know what converges again, but the diverge, the inequality is going to be the same. You would show that the comparison one is less than the original one. The proof works out just the same right there. You just look at the fractions that you've got going on. Now, since this converges, I'm still on this purple star. If that comparison series converges, I need to show again that the original one is smaller. So there's my A sub n. So I'm going to first just write that down. I need to show that this is smaller than the comparison series. Right, so I'll write those down, and that's why I make those look the same right there. So I don't want to just do 1 over 5 to the n, because then those numerators aren't the same. And we'll talk about the homework. Maybe sometimes the numerators might be different, but the denominators might be the same. So we'll talk about a couple things in the homework if they pop up, and you can ask questions on that. But notice when the numerators are the same, you're just comparing those bottom numbers, like that one number example we do. It's the same exact thinking right here, that you're going to justify why this is true. We're going to put true since that 5 to the n plus 3 is greater than that 5 to the n, right? You don't need to justify like, oh, because you're adding 3, blah, blah, blah. Like, just that's the simple stuff that you need. So know your inequality, justify why that's true. And that means if you do that, that means they both do the same thing. So since this one converges, that's why we write that the comparison series down. Since that one converges, this one also is going to converge. And the test that I'm doing here is that direct comparison. So the biggest question I get, actually, let's do one more pitfall I want to kind of mention there, all right? Let's do one more example here. When I look at this example, I'm thinking like on this one, see how that 1 over 3n squared, those look so close to each other. So I thought that proof would have worked out, and it did. I was able to use the direct comparison on that one, all right? But now here's what I'm doing, the same thinking here, as I'm thinking, hey, I got this 1 over n squared in my problem, to use that as my comparison series, right? And so this is going to be a convergent P series. And I'm thinking direct comparison has a shot at working because those look so close to each other. That's why I'm thinking direct comparison might work, okay? It might not work, but let's just see what happens. So since this converges, I'm again on this same purple star. I need to show that the original one is smaller than the comparison one. So I need to write down that the original one is smaller than the comparison one. Now, as you look at that, if that was an n squared plus 1, I could say true, since n squared plus 1 is greater than that n squared, and it would model like that reasoning and that reasoning. But as I write this down, like I said, just because you write it down doesn't make it true. That's what's kind of interesting about some of this, and that's why it's so important that you just follow the steps and you do the good habits that I'm stressing for you here, okay? Just because you write it down doesn't make it true. This is not true. This is not true. Now, because it's not true, don't make up your own rules here. Don't say, oh, that means it has to do the opposite thing. So since that converges, that means that it's not true. So that has to diverge right there. And you start rationalizing, doing your own weird thinking on that. When you start making up your own math there, that's usually not a good sign, right? So don't do that silly stuff, right? All right, so what this means is either you either direct comparison is not going to work on this, or we chose incorrectly for that comparison series. There's nothing really else I can choose for that comparison series, so I know I chose that correctly. And that proof isn't working out. This means direct comparison is not working on this. Now, sadly, here's what some people will do on a testing situation. If they get to something like this on the test, they won't trust themselves that they have their actual test memorized properly. And so what they'll do is they'll flip it around. They'll flip these two things around and say that it is true since the n squared is bigger than the n squared minus 1. Then they're showing this thing when they should be showing this thing. They're trying to show this inequality, and they just don't have their test memorized. So again, half the battle is just having memorized exactly what your test says. So you just want to study that, make yourself note cards, write them all down on one sheet of paper, whatever you got to do there. But make sure you have memorized what your test says. So the way I would do this one, if the direct comparison didn't work, and then you could have went straight to a limit comparison on this one as well, but sometimes that proof works really well. But then I would go straight to that limit comparison, and I got that work already for you right there. So we already have the converge piece there. Remember, your limit comparison, do limits n approach infinity of the original one divided by the comparison one, multiplied by the reciprocal. You're going to get the same degree on the top and the bottom. You get 1. And remember, what you're looking for on that limit comparison test is a finite positive number. 1 is a finite positive number, which means both series do the same thing. And so since that one converged, this one's also going to converge by that limit comparison test right there. So you do run into some weird things, but sometimes if you run into something that's inconclusive, maybe go to the other comparison test, or maybe you take another look at it. Maybe it's an easy n term or something like that that you already know how to do as well. But the number one question I always get is, how do I know whether I'm going to use a limit comparison or the direct comparison? So I try to address it, but limit comparison, if I see polynomials on the top of the bottom, or even stuff with radicals on the top and the bottom, stuff like that, you know, I could do like a limit comparison test on, or if you have something like, yeah, limit comparison test works pretty good on something like that. And also like a UDU integral test works or something like that. So direct comparison, I'm pretty much, like I said, I'm going to jump to that. I'm going to think that it has a shot at working if the comparison series looks so close to each other. Like here, the comparison series is 1 over n. Here, that's your original one. Those look so different from each other. I'm not even thinking about direct comparison, go straight to limit comparison. But if they look close to each other, they have a shot at working. And then right here, we really haven't done limits and stuff with this stuff too much. So you might think, hey, you know, a lot of times I try to use that limit comparison test first, but here we haven't really done limits with stuff like that, or the L'Hopital's rule gets messy with stuff like that. And people a lot of times do illegal algebra with the pluses and minuses and all weird stuff there. So if I have like a number raised to the n, that's the reason where I would jump straight to that direct comparison. So hopefully that kind of helps there. But the nice thing is you got all these other tests at your disposal. So you'll try all this stuff there, and then if something's not working, you go to this, you know, and you can even go to this kind of like just when you think you need to, but there's only a finite number of things that you have to try. So just try some things. If something doesn't work, you got all those tools in your tool belt, try something else there and just be persistent, figure that stuff out.